Hello. In this video I'm going to cover ACE, my assembler code editor, written in Python. I'm going to cover the features and functionality of this application. And this isn't a code review, but I might touch briefly on some of the code itself. So I'm going to start by going ahead and launching my application. And we're greeted with the application here. And some of the things that I kind of felt were required of all editors are just kind of this basic functionality of being able to open, save, you create a new file, this kind of stuff, basic clipboard operations, undo and redo functionality. So just kind of demonstrate that very quickly. So this is a test. Test is actually in mnemonic, but and then we'll go ahead and save that, and let's change our filter. I already have a test, but I'll go ahead and overwrite that. Yes, I want to overwrite that. We can do new, we can do open. This is the test, there we go. I'm going to go ahead and reopen. I'm going to open hello world, and there's my hello world in assembler. And then we also have basic copy and paste functionality, so I can cut this out, or I can paste it in, or I can copy it. So, let's make a selection, and we can copy, and we can do stuff like undo. So I can start undoing my changes, or I can reapply them. So redo, and let's go ahead and discard the changes. Reload hello world, and then we also have basic search and replace functionality as well. So I'll demonstrate that. I'm going to go ahead and put my cursor on line 6, and we're just going to do a search for MOV. So move, and it should find the first occurrence, which is on 9. And it does, it's highlighted. You can see the cursors there as well. And then we can keep clicking that to find the next occurrence. So there's 10. And then, since there's no more after this, we should be prompted to wrap back around. So reach end of file, continue from beginning, yes. And then we wrap back around and we find line 9. And then we can also do replace. So I can replace like LEA, which is load effective address, with, I don't know, maybe a jump not equal. And then so our LEA over here on line 11 should change to a JNE. And there it is. And we can also do a more dangerous replace all. So if I want to change all move instructions to JNE, it's going to prompt me because this is kind of a dangerous operation. So do you actually want to do this? I'm going to say yes, and we replaced it all. But that's kind of garbage, so let's discard that. Alright, so there's kind of the basic functionality. At this point, I think it's probably best to kind of go over the overall structure of the application. So since this is an editor, the main component of this is, of course, the user interface. And the user interface, which is the ACUI here. You can see the files on the top here. The UI is responsible for creating this menu bar, as well as these dockable icon bars, which I think are really cool. This is a feature of PyQt, which is the third-party library I used in creating the GUI here. I looked at a couple others, WXPython, Tkinter, but just PyQt kind of, by looking at the examples and screenshots and this kind of stuff, it kind of had a lot of the functionality that I was looking for. I could see, like, I want to implement something like what that widget is in PyQt. So I'm going to go ahead and redock these. And so that's the UI. You'll see there's a border around this whole bottom half. There's also this, at the bottom you see it when I highlight over these menu items, you'll see the description at the very bottom. Redo last change, or replace a string, so there's a kind of status bar down there. But in this rectangle here, this is actually the edit window. And the editor window actually holds a couple different things, not just this space in which we write our source code. The editor window is made up of the number bar, which is this entity on the left. It's actually completely separate, but it works with. And this opcode window over here, which we can actually adjust this frame. And I will get to that feature last, but we'll talk about that as well. So that's kind of the overall structure. We have the UI, which is comprised of the editor window. The editor window has within it a number bar, and an opcode window, as well as a highlighter. And this highlighter object kind of leads me into the next feature, which is the code highlighting, the text highlighting. This was a really cool feature that I just had to have in the editor since I first saw it way back when learning Viz Basic. Moving out of the DOS world, I remember the first editor that I had that actually had something like this, and I thought it was the best thing ever. So I just had to have that. So what the highlighter does is when the application launches, it loads this color scheme XML file. And the XML is responsible for holding all of the different schemes defined. Now, you don't have to have a scheme defined, and it will default to just regular plain black, not bolded or anything. But if you do have it defined, it will load the instruction set. And you can see here there's actually two instruction sets. There's an example, which obviously isn't an instruction set, but it's here for the sake of showing how it's laid out, as well as to show that this file doesn't get recreated in its entirety. The bottom one is just collapsed, and that's actually the one that we're loading. This version of ACE only supports the 32-bit x86 instruction set architecture. So while I plan on expanding that and including others, I was going to do a flavor of RISC to begin with, but I went ahead and went with 32-bit x86. But all those will be saved here, and it's just identified by the ID attribute of that instruction set tag. So once these are loaded, they're actually loaded into a rule, and the rule is made up of that formatting, and then there are regular expressions for all the different types: mnemonics, comments, numbers, things of that nature. And whenever the source code window is changed, we check to see, okay, is there any text affected, and we do that via a regular expression, which this is a qregexp, which is just part of the PyQt library, but they're just regular expressions that get applied. And so so that's where the formatting comes from, but we can actually change this. So I can either go to format colors, or I can hit my little icon here, and we get the color formatting. And we can change these. And when we change them, it'll actually write that portion of that XML file, that color scheme XML file, for the instruction set that we're changing. So for example, the mnemonic, which is currently set to blue, if we want to change that to, for example, green, we can hit OK, and you'll see it's immediately applied, and that portion of the file is rewritten. So if I come over here to Notepad++, see it's going to tell me, hey, look, it's changed. You want to reload it? And we say yes, and then there's our green. So we have that, and we can unbold it or bold it. You see that changes as well. I'm going to go ahead and change that back to blue. There we go. So yeah, so that's all stored there. The mnemonics are actually also stored in another file. Yes, because I changed it to blue. The mnemonics are all stored in this flat file here, which is prefixed with the instruction set and then mnemonics.dat. So for any different instruction sets that I add, of course, they're going to have different registers. You know, like RISC is going to be R0 through R7. You know, and it's going to have different mnemonics. Some will be the same, but you know, some will be different. And so that'll all be kind of in this DAT file. The last one, which is the x86 ops code, is the last piece of the puzzle. So I think I talked about all the other features of this. So we have text highlighting, you know, we have basic editor operations, but that only makes this, you know, just maybe a smidge better than Notepad EXE, which is fine and all, but what makes this an assembler code editor is kind of this next feature, and there's a whole lot of features that I wanted to implement, but given time permitted, right? So this is the op window, and for those who are unfamiliar with assembler, these mnemonics over here that I'm highlighting, these are the actual instructions that are going to be fed to your CPU to get it to do things, and to do things like add two values together or move a value from one place to another. This kind of stuff. Int 21, like invoking an interrupt. In this case, int 21 is the operating system. Int 10 is, I believe, the keyboard. Things like that, because of course, remember, assembler is an extremely low-level language, unlike Python, which is an extremely high-level language. So these actual op codes are what we're going to see in our executable file, because those are going to be the actual instructions that the operating system is going to feed to the hardware. Now some of these are one-to-one, like this LEA, this load effective address, will break out to a 8D. But others you'll see, like this interrupt, it could be a CC or it could be a CD. It depends on other values loaded in other places, and since I didn't write a compiler, I can't determine exactly what value. So slightly more complex operations like move, while it's just taking values from one place to another, depending on the values and what registers we're playing with, could be a whole list of possible opcodes. So to demonstrate this feature, I'm actually going to load up in one of my virtual machines here a Windows 95 machine, because I did limit myself to the 32-bit OS, so I got to kind of play within that box I've created. And what we're going to do is we're actually going to look at the executable for this Hello World program. Familiar Windows 95 chime. So let's just go down to a DOS prompt and go to Turbo Assembler. I think I called it Hello W. Yeah, okay. So I'm just going to do a type Hello W assembler, and you can see, with the exception of these little comments here, it's the same source code as what we're seeing here. So, you know, model small, you know, we're loading 256 or 100 hex into the stack. So we're going to see a giant blank space for stack. There's our hello world, and then our actual instructions: move, move, load effective address, move, int, and there they are. And we'll go ahead and run hello world, and yay, hello world. And so now we have to actually look at the executable, the good stuff. So I'm going to go into Hexworks, Hex Workshop, and we're going to load that executable. And there's my 256 stack, and at the bottom here is some of our instructions. And so I'm going to actually begin kind of at the bottom working up, just because it's easier. But you can see what I highlighted is that, there we go, is that CD. And sure enough, our interrupt 21 broke out to CD. And so it's going to send that opcode with the value of 21 hex, which, since this is a hex header, we should see 21 there. And actually, if we look 2 lines up, we'll see another int 21, and that's this code right here. Whoops. Uh-oh. Sorry about that. I clicked into the virtual machine and accidentally closed the window. Okay, sorry about that. So if we look, we'll see there's that other int21, and then in the middle is that move command. So if I come back over here, there's that move command, and it's the value 4C in hex, and we're going to move that into register AH. And you might notice that, hey, in this list, B4 is not there. Well, actually it is, and this is kind of one of the things that I was talking about before. Actually, B0 is the value that it got mapped to, but what happened is because B0 is, I think it's to move a 8-bit value into the AL register. B1 would be an 8-bit value into the AH register, but we're moving a 16-bit value, so it's not B0, B1, or B2, or B3, it's B4 actually. So it depends on, you know, the size of the value that we're moving and what register we're moving it into, but it actually did break out into the appropriate opcode, and we can see that right there. So that's pretty much it for now. If you have any questions, please let me know, and thank you.